Hello and welcome to Sidense's webinar on robust NVM solutions. My name is Sean O'Kane from ChipEstimate.com. Today's webinar will be presented by Betina Hold, Sidense's Director of Research and Development. Betina's presentation will cover how the latest 1T NVM developments from Sidense address smart connected requirements with innovative designs for specialty processes and 3D Bitcell designs for advanced process nodes. Betina joined Sidense in May of 2013 and works with the Chief Technology Officer to lead new product definition and implementation. She has over 20 years' experience in semiconductor research and development, holding about 12 patents and co-authoring several publications. Prior to joining Sidense, Betina spent 15 years working in high-tech Silicon Valley, California. Please welcome Betina Hold.
Hello, my name is Betina Hold. I am the R&D Director for Sidense, and I will discuss today how smart connected ICs are driving the deployment of new specialty processes and smaller advanced technology nodes, and how Sidense NVM keeps pace. So Sidense 1T NVM memory macros support the tight requirements for a wide range of smart connected devices. Operation from low voltage sources with limited energy budgets, operation in harsh environments, and robust high reliability operation over extended temperature ranges. Today I will discuss how the latest 1T NVM deployments from Sidense address the smart connected requirements with designs for specialty processes and 3D Bitcell designs for advanced process nodes. So a little bit about Sidense. Sidense is a NVM semiconductor company which produces non-volatile memory. Our specialty is 1T, which is one-time programmable memory. We are based out of Ottawa, Canada. We've been in the industry since 2004. As you can see from the slide, we have over 100 customers, over 600 licenses, over 100 patents, and we have offerings in multiple fabs, foundries, and across multiple process nodes. The smart connected universe comprises devices and systems that have some compute power and are networked, often wirelessly. So if you look at the diagram, you see you have edge nodes, you have hub nodes, and you have sort of a central node. Edge nodes are usually tasked with gathering information. They're small devices, low power. The hub nodes are usually data aggregation, sometimes routing, and then you have the central computation, which takes all the information from various edge nodes, processes, and usually sends data back. It's kind of like an ant farm where you have the worker bees or the worker ants, the drones, and the queen. So there's information going back and forth, or food going back and forth, and that sort of summarizes a connected universe. So these elements all are all parts of various marketing areas. And if you look on the left, domains such as IoT, wearables, mobile computing, medical, industry, industrial, automotive, these all have many, many components at the low edge nodes to the higher levels, and they all have to work seamlessly together. Okay, let's talk a little bit about the demands for a smart connected universe. First of all, you have to address a broad range of process nodes. So depending on what level you're in, if you're at the edge or the compute, or if you're a sensor, they could spread anywhere from the earlier process nodes to the later nodes. You're putting multiple pieces together, and you have to be able to support all of this. Additionally, you have to support low voltage sources with limited energy budgets. Often sensor nodes don't have power supplies. You're working in harsh environments. A car, an automotive, and an engine is hot. You're dealing with high temperatures, high voltages, and you have to be able to support this. The other thing you need is high reliability. You want the pieces to work over extended time and over the extended temperature range. And above all, what you need is most of these systems have to be self-contained and have a high level of security. You want to protect your data, you want to protect your code, you want to protect your IP. You do not want anyone to overtake your system or your data nodes. So let's talk a little bit about Sidense technology itself. So we have a 1T Bitcell, which is a split-channel device. On the right, there's a diagram which shows, essentially, it's a cross-section, so you can see the oxide layer. You have a thin layer and a thick layer, and the thin layer is where the break happens, where the program happens, and the thick oxide is sort of what gives it the current flow. So this is what is actually broken. It is non-reversible. It cannot be undone. It works in a standard CMOS process. It's worked across various nodes, which I'll discuss a little bit later. It's been adopted fairly well over the industry, and it's proven not only from 180 down to sort of FinFET technology, but also across many specialty process nodes, BCD, HV, image sensor, ULP, and RF process nodes. So in addition to the previous slide, which sort of depicts a planar device, we also, with the onset of the FinFET, we catered to the 3D. So on the right, you see a 3D FinFET, which also has a split channel. It's a little hard to see under the yellow, but it's also a split channel device with a thin and a thick oxide. And we have working silicon. And FinFET, the support we have is both for the TSMC FinFET Plus and the 16FFC. Next slide. Okay. So let's talk a little bit about specialty process support and what this means. So first of all, processes vary. Not only do they vary in size, but they also vary in the type of devices. So there are certain specialty processes like a BCD, a high voltage, or the CMOS image sensor, which have special devices, and their characteristics are a little different. So we've ported our Bitcell to all of these specialty process nodes, and we have functional silicon. So what's interesting here is each of these specialty nodes actually carries with it extra features. Some of them are better for leakage, some of them support higher voltages, some of them have higher or weaker DRM rules, and that's what the Bitcell actually can support and be very portable. The other thing is that it's not just the Bitcell. What you want to do is you want to make use of the process features itself. So the Bitcell by itself is portable. We have to optimize the Bitcell, but you also want to optimize the supporting circuit within the IP so that you do take advantage of the high voltage nature of some of the I/O cells in the BCD process, or you can exploit the low leakage characteristics of a ULP. And in the FinFET, you have the stronger PMOS devices. You want to exploit that to get better programming for less overall area and less leakage. So what is this specialty process? It's not just about designing into it. You also have to ensure that the specialty process has results. So first of all, you want to make sure that, within silicon you test and you meet certain requirements. So we are ISO 9000 certified. We have met AEC Q100 grades 1 and 0, which is varying temperatures. You want to have this proven in silicon. And currently we have 180 BCD and 130 BCD solutions out there. So catering to the process, providing supporting architecture is one thing, but really what you want to provide is a system-level solution. So you have a Bitcell, you have a memory which surrounds the Bitcell, supports it. Now, the programming of non-volatile often requires non-standard voltages. That's non-standard from core and I/O. So the read voltages, the programming voltage, could potentially be a little higher, or it could be in between those values. So in order to support the memory macro itself, we create an integrated power supply which actually generates these voltages. To make the system even more usable, we also provide controllers which actually control the two independent IPs so that the user has a much simpler interface. Instead of worrying about how to generate a program pulse, how to create a programming algorithm, we have controllers which actually do this and interface to the IP directly so that it looks like just a regular read-write memory. So one other system offering, which is somewhat smaller footprint, is our SLPMX family, which is also a system. But as this is designed for low voltage applications, no IPS is required. This means it actually can be read and controlled from a single core supply, which is the VDD supply. It still needs an external VPP, but it does not need read voltages. This particular family has memory offerings from 256 bits all the way up to 32K, works at standard core, has a fast read, fast write, and has low power consumption. Controller itself is optional, and the controller turns this sort of single system into an even simpler interface by doing not just read and write, but it can also do other features, which we'll cover a little bit later on. So how do we achieve the low voltage? Part of that is the process, but also part is just special circuit techniques. So in our low power macros, we offer boost options, which is essentially if you supply to the it boils down to the Bitcell on some of the devices. If you can reduce the differential at some of the key inputs to the device, you can get better performance by either lowering the VT of the device or increasing the throughput, the current coming out. So doing this enables you to offer at even lower voltages. The other thing with some of these architectures is we offer adjustable margin circuits. We have built-in DACs and reference generators to adjust the margins for tighter or weaker margins to modify the performance. Some of our other OTP macro designs within our various systems also offer much flexibility. So here's actually a drawing of one of our patents, where what essentially this does is it's sort of a programmable data path. So the macros itself have a single bit cell, but we offer options to read in differential, single-ended mode. We can do single-ended, differential redundant reads, various reads. We have duplicate data paths. We have duplicate outputs, QQN. And what this actually lets you do is, in secure applications, you can actually create duplicate data paths, so you actually have no signatures, and I have a slide on that as well later. But by doing this, you offer not only secure applications, but you can also offer applications where you turn off parts of the data path, so you can save power. But this also lets you have a little more reliability if you want to do a differential redundant read 4 bits for one logical bit. You have a little bit of redundancy, or if you're really concerned about area, you would read in single-ended mode. So the macros themselves, many of them are very programmable with multiple modes of operation, which let you either adjust speed, push your voltage down, and offer both redundancy and security. The other thing you want to cater to in a system is harsh environments. And with all of these process nodes and with our own programming of the NVM memory, we have our own internal harsh environment as well as external harsh environment. So what we do to protect ourselves is we provide various switches and isolation circuits. So if you look here at the diagram, you see we have a high voltage domain, which does the programming, protected from the external world. It's protected from the external world through a switch, and it's also isolated from the low voltage power domain, which is the core domain, by isolation devices. And the low voltage domain also has a switch. So we protect our circuits, the high voltage, the low voltage, internally and externally, so we can work in these harsh environments. We can cater to the specialty process nodes. So building the circuits again, and I mentioned this earlier, and exploiting all the features of the specialty process or the advanced technology nodes doesn't mean much unless you really can show this with testing. So we are ISO 9000 certified. We are working on automotive certif packs. We are enabling ISO 262. We do the AEC Q100 grade 0 and 1 tests. We do provide DFMEA and FEMA reports with scores. With our silicon testing, we run tests. We do the early life failures, the HTAL, the HTSLs. We study the TDDB, so we really know what our NVM memories are capable of, and we ensure that our programming algorithms will produce an NVM which is reliable for over 10 years and has good long-term retention. We also do testing at the higher temperatures, so we go beyond 150. We go beyond 175. We actually go beyond 185. And this is not just about testing. This is not just about software. This is actually about building an infrastructure, building the right boards and jigs and housing and packaging to support the higher temperatures. So we do all of that to prove that we can work reliably at the various temperature extents. Okay, so I talked a little bit about the programming algorithm. So every process really has its custom program algorithm, and this is for the main reason of ensuring you have the reliability and ensuring that the voltage you program at is the most optimal. You really want the lowest programming voltage, but you want to have the strongest program bit cell. So you need to optimize the voltage, the time of programming, the number of programs, so that you get the optimal bit cell, the best reliability, and this is done through silicon testing of many parts, and it's important to have this algorithm because that guarantees the 10 years and it guarantees the reliability of the product. Okay, moving up a little bit. So we have the system, we have the components, we have a controller which facilitates access to the Bitcell, to the macros. But putting it all together, one level which, the whole smart connected universe requires is security. So security is addressed at all levels in an application. It's addressed at the Bitcell, so you want your Bitcell to be physically secure. You want to have security with your macro with your power supply. You want to, within your controller, build secure boot code, other secure key storage features to ensure that you exploit the nature of the Bitcell, the nature of the IP, and make sure you are covered at every level of the hierarchy. So part of the architecture itself, the macro, the OTP Bitcell, the macro itself is tamper resistant. We have built-in redundant or differential modes, and what this does is actually hide signatures. So if you have differential mode, you don't know if you're reading a 0 or 1. We build in self-timers so that tampering with clock speed doesn't expect the read time of the macro. We have built-in hidden ROM rows and test OTP rows, so you can actually access memory outside of the memory space. So if you want to hide certain key codes, you can. Within the power supply, we have a built-in temperature compensation scheme, which essentially what it does is it reverses the temperature effect. So if a hacker is trying to play with temperature to change the performance, the IPS has a switch where you can actually counter-effect that. And we also, within our layout, we do special techniques so that if somebody is trying to do delayering, we create it such that if they delayer it, it actually breaks apart. They can't access the memory parts. Okay, so this is a picture of the Bitcell itself. So if you look on the right, you see it typically, which is an E-fuse where you can actually see the break. Bottom right is our Bitcell, and if you look, there's two Bitcells. One is programmed, one is not, and you can't really tell if it's programmed or not. So what it does is you can't tell if it's programmed, it's not readable, it doesn't leak, so there's no signature. Lighting, UVM, nothing can destroy the Bitcell. It can't be changed through high temperature, voltage, radiation, and it's basically impenetrable to attacks. All right, and I mentioned a little bit earlier about the data path. So by duplicating your data path, you can actually hide it, but it's not just the storage of the data, it's the sensing, it's the data path, and it's the output. On top of that, what you want with the output is to prevent any signature capture, and you want to have features within your memory to reset every clock cycle so that there is no even sequence over time. So we've managed to signature proof our designs, and this is actually implemented in the more advanced process nodes, which is the FinFET design, the FDSOIs. Okay. All right, so a little bit about the temperature compensation, just to explain it in more detail, which is, if you look on the right, you actually see 3 temperature lines. So normally at a higher temperature, you expect higher currents, higher voltage supplies, because your devices just behave that way. So what we do is our power supply works in inverse. So at the higher temperatures, we actually lower the output voltage for read so that it appears that the OTP is actually reading at a lower memory, and this prevents the hacking due to temperature changes. What do we have? We've covered a little bit the Bitcell. We've covered the macros that support it, the power supplies that support it, the RTL controller. So there is a system, but where are we? So if you look here, we have several process nodes that are qualified. We have some that are silicon verified, and we also have some which are in development in the lab. So if you look at on the bottom, you see all the process nodes. We have FinFETs, we have performant HP designs, we have standard GGPs, we have the low power, low leakage, ultra low power designs, we have the CIS, BCD, HV. So we have a gamut of process nodes that we support, as well as going from the larger 180 nodes all the way up to the 16. And then we also cover the higher temperatures. So the automotive requirements are really, really tough, and they do need to work at the higher temperatures. So we have a pretty good process coverage. All right, so where are we going? So this is our roadmap. We have sort of what is available now, we have what is underway, and we have where are we going. And part of where we are going is not just process nodes, but it's also standards. There's ISO standards, there's ASIL, there's FUSA, there's FEMA reports. So we are working on all of those with the advanced nodes and with our various customers. So we have a range of products. We cover automotive, we cover mobile, we cover IoT platforms. We have qualifications to cover all the new ELFRs, the AECs, and we do meet several standards, which I've discussed several times as well. So in summary, there's 3 points I want to hash out here. The first is that Sidense NVM meets the demands of the smart connected universe. We have low voltage, low power operation. We offer high reliability in harsh environments. I've illustrated how we protect our circuits and how we handle various process nodes. We have built-in secure storage and anti-tampering at all levels of the ecosystem, from Bitcell all the way up to our controllers. We have support for specialty and FinFET processes, and we have a roadmap which indicates that we have current, past, and future support for many new processes and process variants, and that we work well with the new technologies that are coming along. So our Bitcell is very portable.
Thank you for attending the Sidense webinar on robust NVM solutions. If you have any questions, please contact Betina directly at bhold@Sidense.com. And for further information about Sidense and their 1T NVM products, send email to info@Sidense.com.